Chapter 13, Liquid State of Matter, Part 1. The big idea in this chapter that in the liquid phase, molecules can flow freely from position to position by sliding over one another. A liquid takes the shape of its container. Let us first, starting by defining what do we mean by pressures. When an object exerts a force on another object, we say that object 1 exerts a pressure on object 2. Pressure could be defined as the force per unit area that one object exerted on another. If you would like to calculate these pressures, is directly proportional to the force applied and inversely proportional with the area. To calculate the pressures equals force divided by area. The units used for the pressures is for the force Newton and for the area meter square. So it is Newton meter square. Sometimes we call it Pascal. Let us try to explain this example. If you look at the photos here, the teacher between nails is unharmed. Explain why. Mainly this is because force is applied over many nails. If we combine surface area of the nails, this is what results in acceptable pressure that does not puncture the skin of the teachers. Now another example. Which position this block exert more pressure in the table? The upright block will exert greater pressures against the table. This is simply because both of them have the same mass, but the area in the upright position is less than the area in the other position. This means that this will exert more pressure than the other one. Air has pressures. Air actually is the mixtures of gases and consists of many molecules: oxygen, nitrogen, carbon dioxide, etc., etc. All these molecules, all these atoms have mass. So in the atmosphere, if you are sitting at the surface of the earth, so there is a column of air above you which contain all these atoms and molecules will exert a force upon you. This is air pressures. And these air pressures will reduce as you go higher because the height of the column will be less. We'll deal with air pressures next chapters, inshallah. Another way of calculating pressures is force per area. There is another way of calculating the pressures. It's a very simple derivations by which we can conclude that pressures will be equal to density multiplied by depth multiplied by gravity. The question clearly demonstrates that pressure is directly proportional with the density and directly proportional with the depth, and the gravity is constant. So if you have more liquid with more dense will produce more pressure than the one which has less dense liquid. And again with the depth is the same. The water tower, which store water and ensure substantial water pressure to many homes it serve, it's also get the benefit of the equations that liquid pressures equal density multiplied by depth multiplied by the gravity. In this case, if the water at high places and the tap waters in the houses at lower one, then the difference in pressures will be push. This will exert pressures on the water on the tape. It will push it down easily. Now, question. When you stand in 1 foot instead of 2, the force you exert on the floor is? Obviously, the answer is the same, because the force does not depend on the area. If we have the question in different way, you also stand on 1 foot instead of 2. The pressures you exert on the floors will be more. Why is more? Because the area which the force applied on the floor is less. so the pressures in this case will be more. The pressure of a liquid at rest will depend only on gravity and the density and the depth of the liquid, as we concluded before. In the liquid phase, molecules can flow freely from position to position by sliding over one another, which means they exert pressures on one another. So a liquid also take the shape of its containers because the intermolecular distance is not tight. It's allow this to happen. Mind you, our body are composed of between 60 to 70% of water. A liquid in a container will exert forces on the wall as well as the bottom of the container. So if we recall that pressure is defined as force per unit area on which the force acts. In other words, in mathematical form, pressure equals force divided by area. So the pressure that block exert on a table is simply the weight of the block divided by its area of contact. The pressure a liquid in a cylinder container exert against the bottom of the container is also the weight of the liquid divided by the area of the container bottom. For the time being, we shall ignore the additional atmospheric pressures. Liquid pressure. The liquid exert a pressure against the bottom of its container, just as the block exert a pressure at the table. How much a liquid weight, and thus how much pressure it exert, this will depend on its density. For the same depth, a denser liquid will exert more pressure than the lighter one. For example, mercury has a density of 13.6 times as dense as water. For the same volume of liquid, the weight of the mercury is 13.6 times the weight of water. Accordingly, the pressure of the mercury on the bottom is 13.6 times more the pressures of water. For any given liquid, the pressure on the bottom of the container obviously will be greater if the liquid is deeper. As you can see in this figure, for figure A, the liquid in the first container is twice as deep, so the pressure on the bottom is twice as the second container. For figure B, two blocks exert twice as much pressures on table as one. The pressure of a liquid at rest does not depend on the shape of the container or the size of its bottom surface. It does not depend on the volume. Liquids are practically incompressible at a given temperatures, so the density of the liquid is normally the same at all depth. So the pressures created by a liquid is given by equations. Pressures will be equal to density multiplied by gravity multiplied by. At a given depth, a liquid exerts the same pressures against any surface. The bottom or side of its container or even the surface of an object submerged in the liquid to that depth. The pressures a liquid exerts will depend on its density and accordingly, the pressure of a liquid does not depend on the amount of liquid, neither the volume nor even the total weight of the liquid. Let us see this example. The water in these two figures, we have two dams which having water behind them. The first figure shows that we have a larger but shallow lake behind with a height. The height of the dam in this case will be 5 meters. The other one, it has small but deep lake with a depth of 10 meters. The dam holding back water twice as deep must withstand greater average water pressure than the other one, regardless of the total volume of water. Notice the thickness of the dam. In the second case, the thickness nearly double to withstand the greater pressure which the water produces on the dam. The pressures of the liquid at Pascal vase, shown in the figure below, is the same at any given depth below the surface, regardless of the shape of the container. The Pascal's vase illustrate that water pressure depends only on the depth and not on the volume. The water surface in each of the connected vases is at the same level, same depth. So the pressure at equal depths are the same. At the bottom of all four vases, for example, the pressures are equal. At any point within a liquid, the forces that produce pressures are exerted equally in all directions. When you are swimming underwater, no matter which way you tilt your head, your ear feel the same amount of water pressures, which means pressure is equal everywhere at that depth. For liquid pressure, the forces against the surface will add up to a net force that is perpendicular to the surface, as shown in figure A. In figure B, which illustrates the effect of the depth, liquid, this is, we have a containers which full of liquid and we have some holes on them. There is hole near the bottom, another one near the surface of the waters, and the other one in the middle. Liquid escaping through the hole initially move perpendicular to the surface. This is indicate that this has a higher pressures. This higher pressure will have more jet. So liquid will nearly move straight in that portion which is near the bottom of the container. It will be the reverse if we go near the surface of the container. So what determines the pressures of a liquid? This is conceptual check. Check your information.